So this session is a tutorial session actually, but there is time limitation. So I have made a presentation for that. I will try to show you the different informations. I try to give you different information through presentation. Sometimes I will access some of the website to show you how data can be available from the internet. Those are free data. So for preparing a hydrokinetic turbine system project, which type of data is required and where we can get those data which are freely available, those things we will do in this particular tutorial. But because of the time duration, because of some limitations, basically you will not do it individually. I will give you these notes so that you will be able to do it individually later. So while we are designing any renewable energy, any hydrokinetic energy project, basically this belongs to hydrokinetic energy project, belongs to a renewable energy source. So first of all, you please see the structure of this hydropower project. What are the different components? So in this particular figure, starting from this upper part, basically it has been shown a conventional hydropower project along with the locations where we can install hydrokinetic turbine. So if we if we go for a conventional hydropower project, so you need to have a dam where you will be creating a certain head which is required for a conventional hydropower. So this dam will be created here and there will be a river channel. So this river will carry most of the water. Sometimes there are some bypass canal arrangement is also made. This river later at the downstream, that can be also diverted. There are different reasons for this diversion. The different structure, civil structure can be just like this type of dam. There are different other civil structure can be implemented here to serve different purpose. Here it is a measuring were given so that you can measure how much discharge is available in this particular open channel flow. Now fluid is flowing in this direction. Here also some of the obstruction through which you can do some of the exercise. Now here if you see in this particular part, here water is tapped from the dam and it is conveyed through a huge pipeline which is called penstock, and it may go to the treatment plant later, which can be sent to the industrial zone, or sometimes it can be sent to the drinking purpose. So based on the purpose, different type of arrangement can be made. So now if you see again, another thing is there is another pipeline you can see here. This is the transfer scheme, that means interbasin transfer. That means say here is excess amount of the water is available here and maybe in near about site where water scarcity is there. So if such type of arrangement can be done so that some of the water which is excess here in this particular catchment or site, that can be transferred to the another basin. So this type of arrangement also can be done through canal or as well as through this conduit, that means pipeline. So different kinds of arrangement will be there. The treatment plant here has been put here in order to soften the water. If hard minerals are present in this particular dam, that can be removed and that can be used in case of these power plants here. Those power plant, it may be nuclear power plant, it can be some other type, or it can be stored in service reservoir. So there are different components. This is a simple representation of different parts which are associated with the power system. Not always all the parts will be present in a particular power system unit, but some of this you can encounter. So here also you can see the water can be again bifurcated from this main channel and some of the water can be passed through here, and here are different civil structure, and just like shoot यहाँ पे this is given, this type of open man-made canal, lined canal, this is called lined canal, that means cemented canal. This type of canal also can be put here. So where we can place our hydrokinetic turbine? Definitely here in this particular part, here basically this particular construction will be used for conventional turbine, just like Pilton turbine or Kaplan turbine or Francis turbine, based on the availability of the head or availability of the discharge. But here if you see this particular structure here, correspondingly if you see this particular picture, then here you can understand that water depth will be less here. But since it is man-made canal, so we can provide slope as per our wish, as per the available terrain. That means if it is the hilly region, so you can provide maximum amount of the slope here. So the velocity, water velocity you will be obtaining here, it will be higher. So it is very much suitable for installation of any kind of hydrokinetic turbine. So this type of hydrokinetic, and since you have seen hydrokinetic, so far you have seen, I have shown you some picture, Sir must have been shown some of the picture. So hydrokinetic turbine, it is a very simple device. So to this particular device, you require the clean water and you require fast water. So if this type of man-made canal is prepared, so we can put some of the strainer so that we can arrest those impurities in the upstream, and then you can allow the water which will be passing through this particular area. So these particular parts are very much suitable. So here this is the part where we can put this hydrokinetic turbine system. Near about you can see there are agricultural area also there. So you can feed this particular water for the agricultural, or vice versa, you can get the water from the main channel for agricultural purpose, and in between you are putting the hydrokinetic turbine, so that you can harness some of the energy which you may use to run the pump which is required for the agriculture, or you may enlighten the agricultural area, field area, where that much amount of the power may not be required, simple lighting purpose. So without the help of the main grid system, electricity grid system, you can use your hydrokinetic turbine to provide the electricity to this particular area. So this type of system we can call, this is the off-grid system. This will not be connected with the main system. So similarly here, this is the region where basically after passing through this measuring area, a small runoff river, just like yesterday I told you, mostly hydrokinetic turbine will be installed downstream of the runoff type of river. So here runoff river scheme, that means this is a earth dam, you can say, huge bigger size of the dam. Here you can see there is a measuring wire. The measuring wire almost will be immersed, and fluid will be passing over the this particular civil construction, so that you will be getting the idea how much amount of the discharge is passing over the wire. So this is for the measuring purpose. Still it is a civil structure. So similarly this is another civil structure which will ensure constant water discharge through the channel. So this is runoff river. So this runoff river is the most suitable where you can use your you can install your hydrokinetic turbine. So similarly, this is the region where I have shown that these are mostly of pipeline, and this is for industry, this is metropolitan city, and after passing through the industry and metropolitan city, still there is some pipeline which is basically going to the wastewater treatment, or it is again after wastewater treatment, it is again enjoying those particular stream which was carrying the main water. So what is this area? This area is basically pipeline. This is not a open channel flow, but these pipelines are already being treated. That treatment may not be such that you can drink this again. That means treatment may be initial level of treatment, but still water flow will be there. So what is this water flow? The water flow is the excess water flow, or after utilization, this water flow we are sending it to the main channel. So drainage, this is actually sanitary water flow. So here also we can install the your hydrokinetic turbine. So if sufficient head is available, head means here we will be converting that head into the fluid flow which is passing through this particular pipeline. So in that manner, basically we can install different types of hydrokinetic turbine with different design in different area of the water source. Okay, some of the area it may be open channel, some of the area it may be pipe flow, but whenever we will be using whenever we will be installing the hydrokinetic turbine in a pipe flow, it should have something different design, so that it will be rotating inside a cylindrical domain, so its shape should be a spherical type. But if you see normal hydrokinetic turbine, either it will be cylindrical type of thing or it will be circular type of thing. So whenever you will be putting it into this pipeline, it must be spherical, so that it's whenever it will be rotating, it should create a spherical domain, so that it can harness maximum amount of the energy. If it is cylindrical, then its size will be comparatively less. I will show you later the picture. So this is the overall layout where we can put our hydrokinetic turbine. Based on this, now we will understand which type of data is required for me if I am going to install the hydrokinetic turbine. Now then we will see where we can find those type of data. So this is the purpose of this particular exercise. Along with this, if you see this particular chart, pie chart, this pie chart I have taken from IRENA, and this particular pie chart, it is giving you a hint that how much cost is required to install a hydropower plant, because everywhere whenever we will be dealing with this type, any type of energy generation system, cost is very much important. So here you can see this is some of the, means you will get some idea. Owner's cost 23%, engineering and construction cost 7%, powerhouse equipment, that means electrical equipment, that is 16%. Penstock, tunnel, tail race, this is a pure part of this this construction. Again, it will be coming under the civil construction. 14%. Powerhouse and shaft, this is actually turbine area, turbine construction. This is 14%. And dam, reservoir, civil engineering, that is 26%. So if you consider the civil construction itself, 26%, and some of the part here 14%, that means almost 40%. And here engineering, procurement, construction 7%, almost 60%. 60% will go for the civil construction. So here benefit of this hydrokinetic turbine is when you are doing this type of exercise. This particular pie chart is for general purpose. So this civil construction will be less. We can invest more amount of the money to the powerhouse and the electricity distribution part. That means that is the savior part. So this is the reason. If you do not have, if you have less amount of the money, if you require less amount of the power, so we can select those type of hydrokinetic turbines. So that is the benefit over the conventional hydropower system. Conventional hydropower system requires huge amount of the money. So those particular parts, whatever I have shown, again I am going back. So I have marked here 1, 2, 3, 4 sort of thing. Those things I wanted to show you through the picture. I tried to collected this particular picture from the Googles, and some of the references also given. So you can see this is not from a single side, this is from the different sides. So dams and barrage, how it will look like. So this is a single Nagarjuna Sagar dam, dam picture is given. Irrigation system, if I want to tap some of the water from the main channel, irrigation system I have just shown you. That was given as a number 1 and number 2 in the previous figure. So it will be looking like this. So it is a bit of smaller diversion, it will be carrying the water. Now you can understand, you can put a hydrokinetic turbine here, sufficient depth, maybe 2-3 meter depth will be there, and sufficient amount of the velocity will be present here. Another example, in Roorkee Ganga Canal, IIT Roorkee near Ganga Canal, there also this type of structure, aqueduct structure is there, and they are also their institute, that means IIT Roorkee also have installed so many, they have experimented so many hydrokinetic turbine in this type of channel. This is very much favorable for doing this exercise. Now here there are bridges where water can be passed through higher elevation. Now the flow gauging station I have shown you where. So flow gauging station, it will be looking like this. Here diverging section, open length and irrigation canal, it is a pure irrigation channel. Line structure may not be there, simple earth structure will be there. So there also you can put your hydrokinetic turbine, and this is the pipeline through which either untreated water or treated water will be passing. So these are the portion. Here you can install your hydrokinetic turbine, but whenever this type of cylindrical passage is there, so if you are putting another cylindrical, suppose if we have cylindrical person, so anyway, I don't have bottle here, I cannot see. Can you give me this bottle? So suppose if this is the cylindrical channel, that is pipeline, it is there. So if I put some of the, again, hydrokinetic turbine here, so what will happen? It will be rotating like this. So whenever it will be rotating like this, if it has a flat surface, top surface here, flat plate, and bottom plate also top, so what will happen? The water fluid will be passing through this top portion. Whenever it will be there, so top portion it will be passing. So it will create some another regime of the flow. So better if we create this cylindrical. So it will be cylindrical wall. So it can occupy maximum amount of the area. So it can harness maximum amount of the fluid which will be passing through this particular area. So its shape you have to modify a bit in order to use conventional hydrokinetic turbine when you will be using it into pipe. So its design will be a bit of different from cylindrical to spherical. You have to do in order to harness maximum amount of the energy. So sort of modification you have to done. So there is another data, again I have collected it from IEA, that from 2021 to 2030 almost 17% of the hydropower energy harness has been increased, and you can understand, you can see this out of this how much is the percentage. Here you have seen from the reservoir, pump storage, run of river. These are the different civil construction where this hydropower energy has been installed. Again, the reservoir from the Africa and Middle East area, and Europe and Latin America, Asia, as well as China. You can see that China is the country who are basically harnessing maximum amount of the energy out of the water resource. So China is leading this particular energy sector. This is a bit of idea, so where you can get data or guideline and research output to deal with this type of energy generation system. So to handle this type of energy generation system, which type of data is actually required? So we have seen the layout of this powerhouses. So if we are trying to estimate how much water is available, so that I can design my turbine accordingly. So first thing, there are different techniques. If there are some sites which will provide you the measured data, river data, discharge data, that is okay. If that is not available, so you can estimate the data, river discharge data, through the terrain and as well as through the precipitation. So how much precipitation generally occurs in a particular catchment, through which you can calculate how much discharge can be available in a particular stream. But that is an exercise of the water resource domain. So still, in order to estimate those water, basically different GIS data is required. GIS data, it may be from elevation, it may be terrain data, it may be different land use data. Land use data means the area you are interested with, whether there is agricultural area, whether there is wetland present, that means another water resource, whether there is a forest or industrial area or your paved lined area, that means the zone where after precipitation fluid will not enter into the groundwater. So whole water will be passing and contributing to the river. So whether those type of area is there, so based on the nature of the land use, ultimate discharge which is coming out of the river, it will be changing. So those type of analysis, basically hydrological or water resource analysis, that can be done through the GIS data, as well as some weather data. So in India, IMD that provides grid based data. So in a particular grid, some degree to by some degree, they are providing the precipitation as well as temperature as well as relative humidity data, through which there are different models. Those models will actually produce predict how much rainfall will be occurring in near future maybe, and then if that kind of rainfall is occurring in a particular catchment area, based on the shape, based on the characteristics, based on the land use of this particular area, you can understand, you can calculate how much discharge is available in a certain point of the river. So those particular exercise can be done. So GIS data will provide you that data. Now discharge is available in this particular area, say. Now while you are installing a particular turbine, you need to have some idea what is the cross section of this particular river, because ultimately you require the velocity. So that particular velocity you can get if the cross section flow area is known to you as well as total discharge is known to you. So you can divide these two, discharge divided by area, so you will be getting the average velocity through this particular area, that means to this particular river or canal. So those type of data also required. So based on this, basically you can set your early goal, that means corresponding to which data you will be designing your turbine. So after that you have to actually, last day also I have discussed, you have to actually scrutinize this particular data, whether the data which is available, this is what is the time series interval, that means whether it is hourly data, each hour data, or whether it is daily data, every day you are getting a single data, or whether it is 10 daily data, that means the measurement which is available within in a 10 day they are giving you one data. So which type of data is available, based on this you can again refine your early setting goal, that means you can come up to a conclusion. Our main aim will be to find out minimum available discharge in a particular area, in a particular channel, as well as you can do another exercise which is for the extreme events, that means flood forecasting. So that flood forecasting is the maximum data, maximum extent of the data. That maximum extent of the data is required corresponding to the failure of the structure which you are going to prepare. One is corresponding to the running of your structure or running of your turbine throughout the year. Another is the extreme point when this your project is going to fail because of this extreme data. So both data we need to know. So for to analyze this both data, basically what is required, different time series data is required. So those data, either time series data which is corresponding to precipitation, that will be available for IMD, or the data which is basically measured through the Central Water Commission, that is available corresponding to a particular river, particular catchment. Or if any one of these two data is missing, so you have to go through the GIS exercise, so you will have some certain kind of estimation, and you have to do some survey in order to get what is your expected location and what will be the cross section of this particular area. How is the terrain, whether you need to excavate this particular area or site, or whether you need not to excavate, where you will be putting your plant, where you will be putting the civil structure, and how you will be distributing your energy, that means electricity which will be generated, if required, where you will be storing the energy in a battery. So all these things you have to do through the field survey. So this type of data is required, and this type of analysis will be done. So ultimately you will be able to generate a technical profile of your turbine, and finally you will be able to predict what will be the supply curve. That means the curve we have seen yesterday, the efficiency curve, as well as there are different sort of curve with respect to time. We can find out how much power can be produced. So efficiency curve I have shown you yesterday, that is the technical profile of your turbine, as well as supply curve, this is corresponding to the electricity, which type of curve will be prepared, and correspondingly you will be deciding whether you will be feeding the peak load, whether you will be feeding the base load, but base load is not possible for this type of turbine, hydrokinetic turbine, in general peak load. So now, after that you will be come to a conclusion, and you will have a decision then now what to do and which type of turbine you will be selecting. So this is again another another picture which will be giving you the idea how you will be estimating. So normal condition, we are putting a dam here on this particular river, and water will be accumulated in the upstream here. This is the downstream, this is the upstream. So differences between the water level, free surface level of upstream as well as downstream, it will give you a gross head. Now you need to carry this water to the powerhouse where your turbine will be installed. This we are talking about the conventional turbine. So while it will be carrying this particular water, so it is actually pipe flow. So this pipe flow will have certain loss, pipe loss. So Darcy-Weisbach equation is given here. That pipe loss will be basically a function of length of the pipe, diameter of the pipe, what is the friction factor associated with this piping lining, and what is the age of the pipe. So this friction factor will also be varying, and if there is any kind of bend or not. So all these things will be defining this particular F value, friction factor, and then you will have a idea how much will be the head loss. And if you eliminate this head loss from the gross head, so ultimately you will get the net head, and based on this net head you will be basically design the conventional turbine. This is for the conventional turbine. Now again, if we are talking about the hydrokinetic turbine, so hydrokinetic turbine, just we told you, so hydrokinetic turbine we are interested only with the river fluid velocity. Now river fluid velocity, as well as I am interested in the cross section of the river, because I have to put my hydrokinetic turbine directly in the river or canal. So I need to know what is the space available there. I need to know what is the water depth assured whole day, whole season. So that particular data, it will be a bit of minimum amount. And if we are talking about the extreme data, so its depth will be maximum amount. So suppose there is a storm event which in generally you have not seen maybe last 5 to 10 years. So that storm event will produce huge amount of the water. So whenever that particular water will be passing through the river, so the depth you will be it will achieve a higher. So if you go for designing with that particular height, rest of the year you will see that your turbine may not be immersed, and your turbine is comparatively bigger, and your discharge which is coming out regularly, that is not sufficient to rotate the turbine, because already I have told you with the weight how your turbine performance will be related. So here I am very much interested about the cross section which is available in the river. Second one is what will be the velocity in this particular river, and if river is big, then in which portion what is the velocity, so where it is favorable to install my turbine. So here if you see this particular picture here, if you consider this is the upstream, this is the downstream, and this is the cross section of the river. So here this is the y-axis, if you consider this is the x-axis, this is the z-axis we represent for the depth. So x and y, this is if you see it from the top, that means top view. Now if we see it from the front view, so it will be yz axis. In the yz axis also, here you will be installing your turbine, or here you will be installing your turbine, or here you will be installing your turbine. That you have to decide. You have to take this decision. How many number of turbine you will be placing here? What should be the gap between two turbine? Whether I can put turbine here x direction also, that means the batch of turbine, whether I can put here, or single set of turbine, maybe 4 or 5 side by side I can put. This is called array of the turbine. Similar type of thing you can see in case of a wind energy wind farm. In wind farm you can see series of wind turbine is installed in a top hill. So there also certain exercise is being made. What should be the inter turbine distance? What should be the arrangement pattern? And I have told you in the last class also, even if the design of wind turbine and this hydrokinetic turbine both are looking same, but there are certain application difference. So that this particular application difference, here we are certain about the direction of the fluid, but the restriction is we will get a very narrow area here, in a narrow depth here to apply your hydrokinetic turbine. So actually you have to find out those things. So here there must be certain measuring technique. Through this measuring technique, basically you will be able to find out what will be the velocity and where is that particular velocity. So those exercises you need to do. Normal discharge, if you want to measure, say you are putting a wire here, just upstream of this particular area where you would like to install your turbine. So through this particular wire you will be getting the idea of the total discharge passing through this particular canal. Now where you will be installing your turbine, based on this particular data you can install your turbine along with this bed depth, you can put the turbine, and you have to decide how much will be the height of this turbine, what should be the diameter of this turbine. So diameter divided by height, it will give you a aspect ratio. That aspect ratio term I have discussed in the last class. As well as if we put a turbine here or maybe multiple turbines here, so how much area it is actually blocking corresponding to the total passage which is available. So that particular ratio is called the blockage ratio. So blockage ratio also have importance while we are analyzing the this turbine. So if we go for the simulation, so what should be the blockage ratio, what should be the aspect ratio? Aspect ratio is directly related with the turbine design, blockage ratio is directly related with the simulation of this particular type of turbine if you are placing it in the water. Those things I will try to show you through SolidWorks as well as your ANSYS analysis, but then also I am telling you those things ki there is time limitation, so I have put it all these notes into a slide, and that slide will be shared later. So even if we go fast, so it will be helping you later while you will be practicing in your home. So we coming back to our calculation, this presentation again. So these are the area, there we can cross check what will be the velocity. So how to measure this velocity? There are different gadgets or devices to the velocity. So suppose if we try to find out what will be the cross section area to measure cross section area, there are different techniques. Simple, you can put a rope like this if your river is smaller. So if you will be getting the width of this particular river. Now you can put the sticks here at a different interval, so you will be getting the different depth. So you can plot it in Excel or any other plotting software so that you will be getting this type of profile. This is one technique. Another technique, you can download satellite data. If suppose you cannot approach this particular area initially, you are not being approached, so you want to do it remotely. So SRTM data, satellite radar topography mission data, those things I will show you a bit of later. I will show you. So satellite radar topography mission data, those things are available in the internet throughout the world. You can select the zone and you can process, you can download this particular raster data, you can process through any GIS software and you can get the cross section directly. But there are particular steps in those particular software. So through this you can find out this type of profile directly. So those are the two techniques. Now once you get the cross section, now I need to find out the velocity. Either you can go for measuring the discharge by constructing a wire. So that is a civil construction, it requires money. With a less amount of the money, you simply bring the current meter. When you are putting the sticks here at a different depth, you also put the current meter. So through this particular current meter, you can record different velocity at a different depth level at different position. So through which also you can get different amount of the velocity. Now there are different other device. Current meter I have shown you, that particular current meter is not here, that current meter is here. Here this is called fish. This is a basically weight. This is a weight which will keep immersed the device. This is actually current meter. Here a turbine rotating type of it will be rotating and it will be creating a pulse. That particular pulse within a minute it will be stored, so it will be converting into that particular rotation into a linear velocity. So in this particular manner you can get what will be the linear velocity in a particular position, and that's this particular fish, it will help. It is a excess weight, it will keep your total device immersed into the water. So this is a current meter. Now here these are the different other device. This particular device, say this is a orifice meter if we are talking about the pipeline. So this orifice meter will give you the discharge. This is a flow meter. This also digital flow meter. This also can be installed in a pipeline. So I can get the pipeline discharge. This is called UFM ultrasonic flow meter. This is a non-destructive type of flow meter. That means this particular orifice or this flow meter, you have to install inside the pipeline. So you cannot take it out, you have to keep it there. So but here this UFM ultrasonic flow meter, this particular flow meter, there are probes. You can put the probes here with the help of gel. You have seen ultrasound means for medical reason people do the ultrasound test. So there also some gel is put and then the probe is given there. Similar type of exercise you have to do it here. And then the pulse will be passed here, another will be received, and ultimately it will be giving you the velocity which will be passing through inside the pipeline. So basically suspended particle carrying through the fluid, it is giving that particular reflection. So through this you will be able to measure this. So all these three are as well as four. This one, this is also a turbine type flow meter. This is actually cut section view of this flow meter. So all these three, this belongs to the flow measurement through the pipeline. And if you wish to install your hydrokinetic turbine in the pipeline. Now last slide I have shown you that there will be a device, current meter. Here there are another device. This is laser flow non-contact type of flow meter, and there is Doppler non-contact type of flow meter. These are also sending the signals and receiving the signals, but these are used in generally for the open channel flow. Similarly, this ADCP, acoustic Doppler current profilometer, that is also can give you a similar type of signal. It will be sending and it will be receiving. So it will also give you the depth of this particular channel, and whenever required it will also give the velocity. So these are the different system through which you can get the river velocity as well as cross section. There are another cross section measurement device, just sonar, lidar, ADCP also I just told you, remote sensing I have just told you, GPS also give you the position, and drone. Through drone taking the picture you will get some idea with the latitude, longitude. So these are all helpful for getting the data of a particular site. Now these are some type of exercise. Now this actually so far we have discussed if we are trying to measure. Now suppose you don't have the facility to measurement. So you would like to take the help from some other sources. So in India there are also sites available. This is India Ruiz government. So this particular site, if we go, so here if you see here in this particular slide, I have given the link in the presentation. Time series data, geospatial data, that means spatial data means geospatial data. Inventory of the water data mentioned in the NIWC, water productivity data, groundwater resource data, all data are available. So time series data, if you click it here, basically you will get this type of search panel where you can find out whether groundwater level, rainfall, river water discharge is required or not. So river water discharge, if I select, and then I can select the state, say here Jharkhand state. If I select Jharkhand state, so district, say Bokaro district, if I select, so I can find out what is the river available here, Damodar river, and then who are the agency, CWC, Central Water Commission, and mode of acquisition, manual or telemetry, which type of gadgets they have used. So manual data, and what is the starting date, which type of data you require. So you can put those data, and if those data are available, so you can download it. So download the data, and download the data. The station was not found. Actually this was given, every possible location is given, and you have to search it whether your particular data is available or not. If those data is available, it is called gauge station. That means data are available. If those data are not available, this is called ungauged station. in case of the ungauged station, you have to go to the site and you have to perform those exercises, whatever I have told you so far. So through this, you will get an idea. So, and that will give you the options to estimate preliminary, and then you can go for the preliminary design, and you can select what should be the reduced scale size of your turbine, so that you can perform within your laboratory. So those type of data you can get this from this particular website. This is one. Now, after getting those data, last day also I have told you, so suppose you have downloaded those data. So those particular data have certain interval. Now through this particular interval, your objective will be to ensure how much data I can get at least throughout the time. So that particular exercise can be done through flow duration curve. The flow duration curve, this flow duration curve, suppose I have got this data. So discharge data, suppose this is the daily data. In daily data, suppose day 1, day 2, this is the data, average daily data in meter cube per second. So this particular data, whenever it will be downloaded from this particular slide site, whatever I have shown you, or suppose you have collected those data. So you can put it day 1 and this particular data. Now actually this data, you have to sort it, and then have to give the rank, and you have to find out the probability of the occurrence of this particular data. That means how many number of the time that particular data will be repeating itself. Say in day 1 you have found 10 meter cube per second of the discharge is available there. Second day you have found suddenly that particular data has been jumped to 21 meter cube per second or meter per second. Maybe third day you have got 15 meter cube per second. Maybe fourth day you have got again 30 meter per second. Maybe rest of the day you have got the data less than 15 meter cube per second data. So at least by observing itself, you can say that okay, fine, the 15 meter cube per second data is almost 80% times is available. So that is, so if I tell that the 15 meter cube per second, then I can tell 15 meter cube per second, that particular value occurrences is 80% of time. So now this is the reliable data. Now based on this data, if I know the cross section, I can divide it, I can get the velocity, corresponding to the velocity I will go for the design. So those things you need to know. And the 31 meter cube per second we have found out, that is the extreme data, say for this particular duration when we have collected the data. So that 31 meter, that is also you have to keep in mind. Sometimes it may happen, it may occur again, maybe very few occurrences, but that can produce extra additional load to my turbine. So my the load bearing capacity of my turbine, the material I am selecting, that should be such so that at least it can handle the 31 meter cube per second of data. In general, we extrapolate the 31 meter cube per second of data to a certain extent. We increase a bit more by through some statistical analysis, so that occurrences of the event we create it maybe 100 year, maybe 1000 year. That is based on the structure. So that language is event which may occur once in 100 years. So it will have a huge capacity. So for this you will be designing your turbine or not, that is up to you. Okay, so you have to take the decision. That is why in the last slide we have told you that there will be some part which is related to the decision. So what will be happening if you are doing it, so this is the particular process if you are doing it manually, but if you are go through the Excel file, so here there is a formula rank. So through this particular rank, what will be, you will be selecting the total data and you will be selecting individual data. So first one, this B2, these things, so once this cell equal to, you have to put it equal to here, equal to sign, then you have to type rank.eq within bracket. First thing you have to select this cell because you want to know what is the rank of this 15 here. So then comma, then you have to select the total data set. So out of this total data set, what will be the rank of this particular data set, and then enter. So it will give you the rank of this particular 15. So it is giving here 17, 18, it is giving the 9, 9th time it will be repeating, 10 it will be 29 time it will be repeating. That means 10 is the safest data. Means if you go for the 10 meter cube per second, the 10 will be, I can say, if 30 number of days is there and 29 times 10 has been occurred. So 10 is the minimum most value. So here I have shown you this data. This data I have plotted here, and here I can see that if I plot it here, so almost 95% of occurrences time it is 10. And if I put here, so almost 0% of occurrence, that means 1% of occurrence, that means once in 100 years, 100 times, so its value will be here 22, like this. So this type of curve will be prepared, that is called flow duration curve. That is also very much important while we are going for the estimation of the availability of the water in a particular river. So these things also can be done. Now I told you, suppose I am not unable to go in a site and I need to know about this particular site, what is the terrain, what is the cross section. So there is SRTM data that is also available. So you can go to this particular slide, copy, and you can put it here. So this particular site will be opening. Now there are two or multiple way to find out the data or download the data. First, you select a region, you can go through the map. Suppose if it's just like we use our mobile, either we put the data, either we put the address data through by writing, or sometimes we put the locator, that through this particular location your delivery boy will come. So similarly, so select a region. Suppose I want to select this particular area, so left click or scroll. So suppose I want to come to Dhanbad. Here we are sitting here. So Dhanbad, this particular area. Now this is the river. Suppose this particular area, Sindri. So this particular left click, drag and release. So this particular area I need to know about the GIS data of this particular area, raster data of this particular area. So this particular area data I can download. So here I can, if I know the latitude longitude, then also I can put it manually, or if I do not know, I can put it like this. So after that, which type of data is required? Here different format of data is required. In general, geotip data, we download geotip data because those particular data are geo-referenced. That means latitude longitude will be embedded in this particular data, and that can be opened in ArcGIS software. Through this ArcGIS software, because you can easily reference those data and you can perform rest of the exercise. I just told you how to find out the cross section of this data. So suppose this is my river in ArcGIS, not in this domain. So if you draw a line, there are certain steps. So it will produce that particular cross section what I have shown you. So those particular exercise can also be done, and finally you can find out to submit. You have to put your email address so that they will know who is downloading the data, and in this particular manner you can get the data. So that is available, fully available, and the resolution of this particular data most probably it is 30 meter. That means the data accuracy is not that much, but preliminary exercise you can perform through this particular data. Now the same thing is written here. Now I just told you that through this data, through ArcGIS software, you can do it. Now you have got an idea that how much will be the velocity there. Now your purpose will be to design for your turbine. Now there are different cross section of the turbine blade may exist. So last day we have discussed two types of engineering turbine we have discussed. One is drag based turbine, drag force based turbine. Another is lift force based turbine. So if we are talking about the drag force based turbine, so its cross section will be in general rectangular. If it is a lift based turbine, so you will find that the cross section will have a aerofoil cross section. This is the aerofoil cross section. So this aerofoil data, where you can find out, there are lots of different shape of aerofoil. You can get this type of aerofoil data from the internet. One of the site is this NASA site, that is NACA aerofoil. In NACA also there are different type of aerofoil, 4-point NACA aerofoil site I have shown you here, and this aerofoil have different characteristics. So this is called leading edge, this is called trailing edge. So if you join leading and trailing edge, this particular length, it is called chord line. And if it is not symmetrical, that means if this particular surface and this particular surface is not symmetrical, so we call it cambered aerofoil. So this camberedness we can find out here through this particular dotted line. So how much is the cambered, that is also embedded in the number here we are putting it here. In this particular drawing it is shown that NACA 2421. NACA 2421, that means first digit 2, this is 2% of the chord length. It is basically giving you the how much is the camberedness, that means maximum camber. So this was the line chord length. From the chord length, what is the deflection of this mean line? So it will give you this camberedness. So this is told that it will be the 2%, that means 0.02 multiplied by the total length. So that much amount it will be shifting from this dotted line. Now where it will be placed with respect to the leading edge. So not only from this particular line to this particular line, but also how much distance from the this tip. So that is given by the this is 40. So that is second digit. So if it is 4, that means 40% of the chord length. If it is 3, that means 30% of the chord. If it is 5, that means at the middle, like this. And rest of the 2, that will be giving you what is the maximum thickness. That means maximum thickness, not necessarily it will be passing through the maximum camber. It may happen, may not happen. So that is why this maximum thickness, that means thickness I will consider this line, this line, this line, this line. So this particular line here, it has been found at the maximum thickness. So that maximum thickness value is given. So using this, a NACA profile has been denoted. So there are different type of NACA profile. This particular NACA profile you can find out from this NACA site. So there is another site. This particular site, if you go to this particular site here, how much will be the maximum camberness, what will be the maximum camber position, if you put it here, so it will generate this type of data set. If you copy this particular link and paste it in the website, you will get those things. So now you can download this. So it will be downloaded into the either CSV file or Excel file, and then you can import it into the SolidWorks or any other solid modeling software. So there you can prepare it and plot it, and then through this particular plot you can again generate the blade, total blade. So this is one process of getting this free data, which has been this NACA data that has been given by the NASA. So those type of data is available in the internet. So through this you can perform your analysis. So anyway, next half we will start with SolidWorks exercise with an example of a hydrokinetic turbine, and I will try to describe how we generally prepare those type of drawing. Okay. So these are the references here, and thank you for this session. Okay, and next session we will start it again